Okay, let's get started. So thank you for coming along today. Last week, we looked at correlation and bivariate data analysis, and I spoke about how we, in statistical inquiries and also scientific inquiries, often want to figure out whether change in one variable can explain change in another. There was, at the end of last week's session, some discussion about the difference between what we call correlation and causation. And I thought I'd start just by introducing two other spurious correlations, is their proper term. So what I have on the screen here is, on the x-axis, we have the independent variable, chocolate consumption. And then we have the independent variable, the Nobel laureates per 10 million population. So what does this look like? Well, it looks like a scatter plot. Each of the countries have been given, so Japan, for example, has just under 2 kilograms per year per capita of chocolate consumption, and they have between 1 and 2 Nobel laureates per 10 million population. And then all the way over here, the Swiss, wow, they're going good, not only in chocolate consumption, but also winning those Nobel Prizes. So you might think, let's put a line of best fit through this and see if we can figure out how much these two things are correlated. And if we did, we'd probably find out that there was a strong positive correlation between these two variables. However, does it mean that eating more chocolate helps you win Nobel Prizes? If only. Just because we can put a line through something and show that two variables are related doesn't mean that one thing causes another. I've got another one, which is probably my favorite, which is plotting the number of pirates there are in the world against the global average temperature. So back in the 1820s, lots of pirates everywhere. These days, very few pirates. Notice that the numbers on the x-axis are going down. So as time has gone on, piracy, at least, sail in the high seas, yar me hearty kind of piracy has gone down, but global temperature has gone up. So does that mean more people need to resort to piracy to address global warming? No, it doesn't. Of course it doesn't. So that, I just want us to keep that in the back of our mind whenever we're doing any bivariate data analysis. We aren't showing that the independent variable causes the dependent variable to change. We're just trying to figure out whether the two things are linked. Whether or not there's a causative relationship between the two variables is a question for the scientists. For us as mathematicians, our focus instead is going to be to figure out the strength of this kind of relationship and whether it merits further study. That's something that we can leave to the scientists. Okay, so today we're actually going to be exploring a few ways to use technology to generate the line of best fit and figuring out how strong the correlation is. And then once we've got this line of best fit, what can we do with it? And the answer is we're going to use it to make a range of predictions. Okay, so let's get started. I'm just going to zoom in here a little bit. Zoom. Okay, well, let's zoom in a bit more. There we go. So imagine yourself a store owner. You are writing down the date, and then at the end of the day, oh, you sell ice cream, by the way, I should have said that. You sell ice cream. You write down the date, and this is in January. And at the end of the day, you write down how many ice creams you sold and what the temperature was, the maximum temperature for the day. And let's just take a quick look at the data before we do anything serious. So when the temperature was Cold, 12, 11. Sales were relatively low, hovering about the 100 mark. I've got this 15-degree day that only sold 41 ice creams. Terrible day. But here, at the end of the week, it got really hot and huge number of sales, like more than 3 times what it was on the 11-degree day. So as a fine purveyor of ice creams, you might think to yourself, on this day when it was 15 degrees, maybe there was a whole bunch of ice cream that you made that's not fresh anymore and you can't sell it. Or maybe there was a bunch of cones that you made, ice cream cones, and they're going to go stale. And you're thinking to yourself, I'd like to know if I can look at the weather forecast the night before and find out what the temperature is going to be. Maybe I can use that to predict just a rough estimate how many ice creams I'm going to sell. And that might affect whether or not I call in another staff member. It might affect how much ice cream I get prepared. And it's better than having no prediction at all. So before we do any of this analysis, the first thing we need to decide is which is the independent variable and which is the dependent variable. And those words sound so similar. They only change by the in at the front, dependent and independent. And I think a good way to sort out which is to try writing out both of the variables in a sentence and seeing which one makes sense. So I'm going to try them out around both ways. So I'm going to try it around the way that I see here. Ice cream sales depend on temperature. I'm going to try it the other way. Temperature depends on ice cream sales. Which one of these sounds right to you? Does ice cream sales depend on temperature? Or temperature depends on ice cream sales? I think the first one makes a lot more sense. And that's because the temperature isn't going to change if people buy more ice cream. Instead, people might buy more ice cream if the temperature changes. So because the ice cream sales are depending on the temperature, this is the good one. This one is the not so good one. I can then say that the ice cream sales is the dependent variable because it depends on the temperature. If it was the other way around, temperature would be the dependent variable. That's not the case here. So if you're trying to figure out which one's the independent and which one's the dependent variable, try and put it in a sentence and see which one makes sense. And we'll have a bit more practice of this as we go. If you're from a place that uses the phrases explanatory and response variable, instead of depend, put responds to. Ice cream sales responds to temperature, rather than temperature responds to ice cream sales. And because ice cream sales respond to temperature, ice cream sales are the response variable. Okay. So now that we figured out that ice cream sales is the dependent variable and temperature is the independent variable, what that means is the independent variable always goes on the x-axis. So this is going to be our x value and the sales are going to be our y value. Independent on the x-axis, dependent on the y-axis. So before I go any further, the columns are the wrong way around. We always write our x variable before the y variable. The person who was the ice cream shop person probably hasn't done any bivariate data analysis before, so they don't know which order to put the columns in, but we know. We're mathematicians, and we say, well, your temperature is your independent variable, so it should go as your x-axis. So thanks to the magic of spreadsheets, I'm just going to click and drag this across. And now my X and Y columns are the right way around. So let's do some bivariate data analysis. In order to do this, we're going to have to enter it into some form of technology. You might be using a CAS calculator. You might be using some specialized software. What I did was I went online and I looked for an online correlation calculator, and I found this one that Casio provides. So this will be very similar to the interface that you have on whatever piece of technology you choose. And if you look up, the proper name for it is linear regression. It sounds a bit scary. We've already got so many words flying around, but if you type in linear regression calculator, or even something like line of best fit calculator, you'll find plenty of things on the internet that will do this calculation for you. So the nice thing about this particular one that I found is I can just copy the data here, now that I've got it in the X and Y the right way around, and I paste it into here. If you're using a CAS calculator, you might have to type all the numbers out one by one. But I have all the X values in and all the Y values in, and then I click execute. And let's see what we come up with. Okay, the picture down here, I'm going to zoom in a little bit, shows me my line of best fit. And we can see from this picture that these are our data points. These 2 points are our hot days, the ones that came at the end where we were getting nearly 300 or over 300 sales from the hot days. Because these ones down here, these are our low temperature days. And that makes sense. If it's 11 degrees out, you're probably not going to buy ice cream. If it's 38 degrees, you probably are. So what is the stuff that's coming out here? Now, depending on your technology, you'll have different outputs. But the one thing that you'll notice is this number, which is called the correlation coefficient. And we discussed that last week. The closer this value is to 1, the stronger the correlation is. If all the points lie on a straight line, so you draw the line of best fit and it goes through all the points exactly, the correlation coefficient is exactly 1. But here, the correlation coefficient is 0.9. 0.9 is still pretty good. There's a good visual guide in the textbook, which will help you understand in the Mathspace textbook. I think it's in here. Here it is. So, zoomed in too far. Let me zoom out again. And now I scrolled too far. Sorry about this, everyone. There we go. So the correlation coefficient here, if we are up in this direction, the value is near 1. We have a strong positive linear correlation. As we get more towards the 0.5, that's when we start talking about moderate. Below 0.5, that's weak. 0 is no correlation. And then when we start getting negative values, that's when the slope of the line goes down. That's when we start having weak and then moderate and strong as we go down, down, down to -1. So in this particular case, we can say that the correlation is strong, and that's what we should expect. This person is selling ice creams, and people buy ice creams when it's hot. That seems like a fairly reasonable thing to say. But then we get these two values, A and B, and it's something that is universal amongst all these kinds of technologies and calculators, that we have A and B where we write it the wrong way round. I don't know why statistics people do this, but it's just the way that it's always been done. It's a matter of mathematical history. But notice that the A value is actually not the number that multiplies the X. We're used to Y equals mx plus B or Y equals mx plus C. The thing with the X always comes first. But in this particular case, it's coming second. So your calculator will probably tell you how to match these things up, but I'm going to transfer these results over to my spreadsheet. Here we go. So that's my value of A and B, and the calculator is telling me that it's A plus BX. So I can then write that as Y equals minus 25.427. Let's round it to 3 decimal places. Plus 8.991x. Okay. So this is our line of best fit. What we're going to do now is we're going to see how to use this equation. We can, the whole point of doing this was to give the person running the ice cream shop some idea of how to predict their sales based on the temperature. So over here in this part of the spreadsheet, I'm going to put temperature and sales. And this is going to be my prediction. So I'm going to show a few tricks on how to use spreadsheets. I'm just using Google Sheets, but you can use Excel or any other spreadsheet program. So I'm going to start off temperature at the lowest temperature that I've recorded. I'm going to put 11 here, and then 12, and then 13. And instead of typing all the rest out, I'm just going to click and drag. There we go. So now I have a bunch of temperatures all in a line. Now I need to figure out how many sales I'm going to make. And I'm going to use this formula that I have written here to make this prediction. The sales is the Y, so Y equals this thing. So I need to do this operation, minus 25.427 plus 8.991 times the value in this column. I'm going to write that out like this. If this is the first time you've used a spreadsheet like this, then I highly recommend it. Someone once said that there are 2 certainties in life, death and taxes. I think these days there are 3 certainties in life, death, taxes, and spreadsheets. Whatever job you get, it's gonna have a spreadsheet in it, I guarantee. Like, I got some tradie friends, they do spreadsheets too. All right, so sales equals minus 25.427, which is just the number that I got out of my calculator, plus 8.991, and then to do a times, I do the asterisk symbol, which is usually Shift 8 on a keyboard, because you can't do a cross. Times, and then instead of writing X, I'm going to write the reference to this cell. So this cell in the spreadsheet lies in column F, row 3, so I write F3. And if you do that right, it should highlight the cell that you're referring to. And I hit enter. So this is the same value as I would get if I wrote equals minus 25.427 plus 8.991 times 11. I get the same value as if I type F3. But the cool thing about doing this cell reference is that I can do the click and drag trick on this cell, and it's going to change it. So now when I look at this cell, notice that it says F4 instead of F3. That's because it's now moved down and it's reading this cell instead. And I can do it again. 91.456. And that's reading off this one, 13. So it's kind of doing the substitution for us at each step. I substitute 13 into this formula, x equals 13. What's y? This thing. What happens if I substitute 14 and so on? I can just click and drag all the way through. And there we go. All of my predictions. So the person who runs the ice cream shop, they hear on the television, tomorrow is going to be 26 degrees. And according to these observations, they should expect around 200 sales. If they hear it's going to be 36 degrees, it's going to be around 300 sales. There are a few other things that we can see from the predictions. How much does the prediction go up by each time the temperature goes up by 1? It's a bit hard to see because of the decimals, so just ignore the decimal part. 73, 82, 91, 100, 109, 118. When the temperature goes up by 1, the number of sales goes up by 9. Where did we see 9 or a number close to 9? Ah, yes, that's the gradient that we got for our line of best fit. So this number that we get out of our calculator, the gradient of the line of best fit, tells us on average how much the temperature change by 1 is going to influence the sales. Temperature goes up by 1, sales should go up by 8.991. If the person hears that it's going to be a 40-degree day, then it's 334.213, sure, but it's going to be a huge day. But before we did all this analysis, all that the ice cream owner would know is that it's cold. I'm not going to sell much. It's hot. I'm going to sell a lot. But this actually helps them put some numbers to it and figure out how much they need to prepare, and it helps them avoid waste, which is really useful, especially if you're running a small business. Okay. So each of these, the Y-intercept, we'll come back to that. The next thing I wanted to, let's do it again. And this time I'm going to go a little faster so you can see what I'm thinking, the process from start to beginning, start to end. A scientist is observing a cricket. This is the kind of thing that scientists do. And they take a look at the temperature, and then they figure out how many chirps is the cricket making. And they make an observation, which is, if I increase the temperature by 3, you can see them increasing the temperature by 3, the chirps are going up. It seems like the hotter it is, the more that the crickets chirp. Okay, I want to see if I can make some predictions. So in order to do that, I'm going to go back to my same calculator that I was at before. I'm going to clear my old input, and I'm going to copy this new data, copy, and paste it into here. Paste. And then click execute. And we'll see what kind of a line we get this time. Oh, look at that. All of the points are lying very close to a line. Okay. So let's take the A and B values, just like we did last time, and see if we can use it to make a prediction. Okay. Go over back to our spreadsheet. This is our A and B values. And remember that this is the equation. And as I said, this will almost certainly be the same for you for whatever piece of technology you're using, y equals a plus bx. I'm just going to paste that in there just to make sure we know what these numbers mean. And so we can write out our prediction line, and it goes y equals minus 55.586 plus 9.741341. There we go. Oh, I've got to put the x on the end. X. So this is our prediction line. We're going to use this to make some predictions. I'm just going to copy these across, temperature and chirps per minute. And for reasons that I will explain in a little bit, I'm going to start with 14 and 15 down the page a little bit. So 14 and 15, and let's go up to, let's just go up to 24. Okay. So this is our temperature and our chirps per minute. And we're going to put the formula in just like we did before. So I'm going to say that this cell, F13, is equal to minus 55.586 plus 9.741, and I'm doing the shift 8, the star asterisk symbol, to get a times, and then I write the cell reference, E13, and it helpfully highlights and says, yep, that's the cell we're looking at. Okay. And then I fill this down, and I can see that when the temperature is 14, I predict that it'll be about 81 chirps per minute. Now that's not what we saw, but still, it's a prediction based on all of the data that we have so far. Generally speaking, a line of best fit will not go through most of the points. This is just the line that we can see down here on the calculator. As you can see here, 14, it's a little bit higher than that data point, which is why we end up with 81 chirps per minute instead of 77. But notice that I only filled the table from 14 to 24. Why is that? Well, we can actually fill upwards as well. Oh, sorry. At least I thought we could. Yeah, there we go. And we can fill up, fill down as long as we like. Let's just go like this, because this is a straight line now. It goes infinitely in both directions. But this is where we start to go, maybe our predictions aren't so good. So when the temperature is 4 degrees, the crickets are going to be making minus 16 chirps per minute. That doesn't make any sense. So this isn't making much sense. And up here, like, if the temperature is 70 degrees, I think the cricket's getting cooked. I don't think it's making, well, like you could just imagine it going, just chirping more and more, but it's probably not going to be making 600 chirps per minute. It's probably going to be cooked. So there's something special about the range that we started with between 14 and 24. In this range, our predictions are kind of just filling out the space in the data that we already have. Once we go outside this range, and let's just color it a helpful color. Once we go outside this range, that's when we start to be a lot less sure about our predictions on either side. And this makes sense too in the ice cream example. Let's go back to the ice cream example and keep filling that table. So let's say it is 100 degrees outside. Oh, Going to sell 800 ice creams today. No, everything is on fire. So you're not selling any ice creams today. We have a special name for predictions that stay within the original range. So here, the smallest value was 11 and the largest one was 38. So between 11 and 38, this section of the data, you can think of it as like filling in the gaps between the data that we already have. And this is called, its special name is called interpolation. Inter, because it's within, polation, because that's the word, interpolation. But it contrasts with all of this. Once we go outside the data range, we call this extrapolation. Now, extrapolation is a word that is in common use. You've probably heard someone say, let me extrapolate, or that's an extrapolation, or something like that. And that's where the word comes from. It means going outside of something that you currently have a good understanding of and continuing the reasoning into new and undiscovered realms. But so the interpolation zone is safe. We can make predictions there, but the extrapolation, that's where our predictions get a little bit weak as well, instead, I guess. And in the lesson, there are some good images here. So if these were our data points and we've generated the line of best fit, then if we're making predictions, and I can see that I've taken the smallest X value and the largest X value, if I am making predictions, it just means take the X value and find the corresponding Y value. These are interpolations because I'm inside the range of data that I originally had. I could imagine there being a dot here or a dot about here. But when I start going outside that range, that's when I have an extrapolation. And I'm no longer nearly as confident that something else that I might not have accounted for is starting to crop up instead. So in summary, when we make a line of best fit, we can tell how good the prediction is going to be based on the correlation coefficient. The higher the correlation coefficient, the closer the points are to a straight line. So if I need to figure out what 19 is, it's probably going to be really close to this line. So that's one thing to keep in mind. The closer the correlation coefficient is to 1 or to -1, the better our prediction is going to be. At the same time, we also need to be careful of where our prediction is occurring. If it's occurring inside the original range, we call that an interpolation, and it's much better as a prediction than trying to interpret outside the range. Okay. So with that in mind, I'm going to do a few Mathspace questions and see how I go. So I'm going to zoom out a little bit. So this first question here has a bunch of data points on it. And it has a line of best fit already drawn. I need to determine the gradient of the line of best fit. Now we could find out all the X values and all the Y values, put them in a spreadsheet, take that spreadsheet and put them in the formula, in the calculator, and then read off the gradient from the table. That's too much work. Remember that a line is a line is a line. If I want to figure out what the gradient of any line is, I can always do rise over run. To do rise over run, I just need to pick a run. In this case, I'm going to pick 0 to 10. And I can tell that at 10, the value is 3. And at 0, the value is 19. So what's the rise from here, this point up here, down to here? Hint is in the down. It's not a rise, it's a minus rise. So between 19 and 3, I lose 16 in height. And I divide that by the run, which is 10. Okay, correct working step. I've got to simplify this fraction. Minus 16 on 10, I can divide the top and the bottom by 2, so minus 8 on 5. So that's my gradient. I could write it in a decimal as well, and Mathspace would accept that, of course. Find the y value of the y-intercept of the line of best fit. That's this one up here. I already found it. So remember, a line is still a line. We might have used points to generate it, but it's still going to have a gradient, and it's still going to have a y-intercept. So for this particular question, the y value of the y-intercept is 19. Determine the equation of the line of best fit in the form y equals mx plus b. Well, we've already had it laid out for us, which is good. We have the gradient, we have the y-intercept, so my answer is now y equals minus 8 over 5 times x plus 19. Cool. So this was just to reinforce the fact that we always get a line when we do a line of best fit, and it has the same sort of properties that any other line has. Okay, let's move on to a slightly more ambitious question. The forecast maximum temperature in degrees Celsius and the observed maximum temperature are recorded to determine the accuracy in the temperature prediction models used by the Weather Bureau. Using a graphics calculator or other technology, calculate the correlation coefficient between these temperatures. Give your answer to 2 decimal places. Okay, before we do any maths, let's think about what we're trying to achieve here and what our result might mean. We have our x and y laid out for us. I can see that the forecast values are along the top. That is our independent variable, and the observed y value is the dependent variable. I actually think that this is round the wrong way now that I think about it. Because anyway, we'll roll with this for now. If the correlation coefficient is very high, what does that tell us? The correlation coefficient is how close the points are to a line. And if those points are all very close to a line, that would be good. And what's the best case scenario? I'm just going to draw it out for us. So I've got my forecast. I'm just going to write forecast. And this is actual. So let's say that the Weather Bureau was 100% accurate every time. If they forecast 19 degrees and they're 100% accurate, then the actual should also be 19. Like so. If they forecast 20, then the actual should be 20. If they forecast 21, the actual should be 21, and so on. And all in all, I end up with a line that is y equals x. Whatever the forecast, that's the actual. That would be the ideal situation if all of the points, if all of the predictions were accurate. But let's say we have a rubbish weather bureau. What would that look like? Well, that's when the points are all over the place. They say it's going to be 30 degrees and it turns out to be 15 degrees. That's that point. They say it's going to be 5 degrees and it turns out to be 50 degrees. That's up here. And we've got points all scattered around. If points are scattered around, we know that the forecast is not good. And we'll be able to tell that by the value of the correlation coefficient, because the correlation coefficient tells us on average how close are these points to this line. So let's calculate the line of best fit and the correlation coefficient along with it. No matter what piece of technology you're using, the correlation coefficient will almost always be calculated at the same time as the line of best fit. Okay, so I'm going to clear this and turn this off. Now, the unfortunate thing here is that my values are going across when my calculator is going up and down. So I'm going to do split screen here. And I'm going to type, oops, this is the one I'm looking at. And I'm going to type them in as I go. So 29.8, 27.1. Oh, sorry, I'm already making a mistake. 29.8 is the X value, 31.1 is the Y value. 27.1 is the X value, 27.7 is the Y value. 27.1 is the X value, 24.3 is the Y value, and so on. I'm going to assume that you can see to the end of this particular section. I click the button and it's going to tell me what the correlation coefficient is. Now I'm going to cheat and I'm going to ask Mathspace to tell me what the answer is, and we're going to think about what the answer is. So if I'd continued on with this calculator, I would have gotten an answer, and I round it to 2 decimal places and I get 0.85. Anything bigger than 0.8 is actually pretty good. If you this data, I believe, is taken from actual data, and 0.85 is doing pretty good for the Weather Bureau. So now we need to figure out what kind of relationship it is. And we can tell that from the value of the correlation coefficient. The first thing that we notice is that it's positive. So that means that we can rule out the negative relationships. It's not a negative relationship because this number is positive. If the correlation coefficient is positive, it's some form of positive relationship. How strong? Well, if it's close to 1, like this is, it's strong. If it's close to 0.5, it's moderate, and if it's less than 0.5, it's weak. So in this instance, it's a strong positive linear relationship. It's positive and it's close to 1. Use your calculator to form an equation for the least square regression line of y on x. Give all values to 2 decimal places. Once again, I'm going to pretend like I put all the values in here and got my answer out, but I'm just going to repeat the same caution that I gave last time. Almost always, the values are not the way around you think they are. The first value is the Y-intercept and the second value is the gradient. Blame statisticians. It's not on me. So I'm going to once again, thanks Mathspace, you're going to tell me the answer here. Okay, y equals 0.89x plus 2.81. Remember back when I was first describing this problem, I said that the ideal case would be the line y equals x. But what instead we have is we have a line that's a little shallower than y equals x, but it starts a little bit higher. If I were to draw that out, it'd look like this. So I've got my axes, 1, 2, and I'm just going to draw the line y equals x. Oh, no, I'm not. I'll get my pen out. Here we go. This will make it easier. So I don't draw a terrible line. Yeah. There we go. So that's the ideal case when we have super accurate predictions. But what we have instead is it starts a little bit higher, 2.81. So it starts about here. And because its gradient is 0.89, which is less than 1, this line has a gradient of 1. It's a little bit shallower as well. And that green line I've drawn is the line of best fit for the data points that I had above. So now we can make our own prediction. Oh yeah, weather people, you say it's going to be 27.2 degrees. Well, I'm going to correct for your bias, and I'm going to use this green line to fix it up. So 25 degrees, they say it's 25 degrees. So here it's 25, say. I don't actually think that it's going to be 25 because I think you overestimate hot temperatures. So instead, when I go up to here and go across to there, the value I find on this axis is going to be my prediction based on your prediction. Okay. In order to find this value, we just need to substitute this value for x in here. 0.89 times 25 plus 2.81. Correct. And in the interest of getting to the final step, one more question before the end. I'm just going to skip the calculation. Thanks, Mathspace. Final question. For which of the following forecast temperatures would the regression line produce the most reliable prediction? Okay, we already figured out that the prediction was pretty good up here. We got 0.85. But this question here is asking us about whether or not our prediction is going to be an interpolation or an extrapolation. Once again, I'll refer you to the chirping crickets, where they certainly aren't chirping when it's too cold, and they're definitely not chirping when it's too hot. We want to know our prediction is always most accurate when it is an interpolation. And we tell that by seeing whether or not the x value lies between the original values in the data set. So what is the range of values in the original data set? What's the lowest number I can find up here? It's 27.1. And what's the highest number I can find? 37.2. So if I want to make a prediction and it's between 27.1 and 37.2, that's the interpolation range, and that'll be the best kind of prediction. If it's outside the range, it'll be an extrapolation, and that's automatically less good. Out of our options here, x equals 25, that's below 27.1, so that's going to be an extrapolation in the negative direction. X equals 39, that's an extrapolation above. So instead, x equals 35 is going to give me my most accurate prediction because I'm in that interpolation range. Cool. Got a few more minutes. I'll see if I can do one more. The price of various second-hand Mitsubishi Lancers are shown below. Find the equation of the least squares regression line for the price in terms of age. The best thing to do in this instance is, of course, throw it into your calculator or throw it into your software. Let's see, there's 10 values. Yeah, okay. I'll just do it nice and quickly. I want to actually do it properly this time, not just say, yeah, let's not say I did. Okay, let's do it. So x is 1, y is 1600. X is 2, y is 1300. X is 0, y is 21990. X is 5, Y is 10,000. 7, 8, 6, 0, 4, 1, 2, 5, 0, 3, 1, 1, 0, 4, 1, 1, 0, 8. It's not very much you got for that car. 4,500. 2, 1, 4, 5, 0. Okay. And execute. And it's going to tell me, here's my line. Now, obviously, we can already tell things like interpolation and extrapolation. You could get $22,000 for a Mitsubishi Lancer that's minus 2 years old. Okay. Yeah, so that's the extrapolation. But we can see that the older the car is, the less money you're going to get for it. Notice that the correlation coefficient in this instance is negative. So it is a negative correlation, which is what we expect. It's also close to 1, so this is a strong negative correlation. And these two values are our values for our y-intercept. And once again, remember that it's the kind of the wrong way around from where you'd expect it to be. So y equals 18407, 18407, and then minus 1694, because I'm rounding to the nearest integer, minus 1694x. So I just rounded each of these to no decimal places, to the nearest integer, and I substituted them into the formula the right way around. Classic mistake to get them the wrong way around. Okay. State the value of the y-intercept. Once again, this is that situation where this is just a line. The line doesn't know it's being used to value Mitsubishi Lancers. It's just a line. It just has y-intercepts and gradients just like every other line. 18407, because it's the value that's not multiplied by x in the line equation. The value of the y-intercept indicates that when a Mitsubishi Lancer is brand new, its original value is, on average, how many dollars? 18407. Now, of course, we already have one data point, which says that a Mitsubishi Lancer is 22 grand. That's just how much a new one costs. But we are not reading from the table, we are reading from the line. And you can see here that this is the brand new price, and this is the line that's going through it. You might start to think to yourself, this doesn't make a lot of sense. And you're right. Last week, we talked about how there are different kinds of lines that you might want to fit to data. In this instance, maybe something that curves a bit might be the best way to fit the data. But we're just sticking with lines, and we're the mathematicians. If someone tells us to fit a straight line to something, we'll fit a straight line. And we'll talk about the rest later. So on average, we should expect that from the model, from the linear model. Does the interpretation in the previous part make sense in this context? And so when the explanatory variable has a value of 0, this is within the data range, and the value of the dependent variable makes sense. That's true. We are not extrapolating here. We have an age 0 car, so we're not going outside of that green zone into the red zone. It might not make sense for other reasons, but it makes sense when we're comparing interpolation and extrapolation. State the gradient of the line. That's this one, minus 1694, minus 1694. And let's think about which of these is true to finish. There's a lot of jargon here, but let's think about what the gradient means before looking at these options. Each year, so this here, this part C is telling us that on average, at the start of its life, the cars are going to be worth 18,407. Then if I put in X equals 1 here, that's 1 year after it's brand new, it's going to lose this much value, 1694, it's going to go down. It's going to go down by that same amount the next year, and the same amount the next year. This model is telling us that on average, the car is going to lose $1,694 each year. Now, of course, there are limits. A 100-year-old Mitsubishi Lancer, probably not going to work in this context, but we can think about it as being each time the top variable goes down by 1, oh, sorry, goes up by 1, the age goes up by 1, the value goes down by this amount. Let's see if we can find an option that says that. If the explanatory variable increases by 1 unit, then the dependent variable decreases by 1694 units. So the top variable increases by 1, then so the age goes up by 1, then the dependent variable, the price, because the price depends on the age, goes down by 1694. Okay. So this has been an intro into all the different things that are involved in bivariate data analysis. Next week, I will pick a new topic to talk about, something in the senior secondary space. So send me an email by replying to the feedback form, and I'll take your suggestions into account when thinking about what we'll look into next week. So thanks for coming along, everyone, and I'll see you next time.